Sí, pero no puedo entrar de ahí porque es una cosa técnica. No puedo.
Ajá,
Ajá.
pero te la puedo compartir.
Me puedes dictar rápido la ID de la reunión y ya.
Buena pregunta. A ver, no sé si
Es que
alguien
no
por
la pude encontrar, por eso te la pido.
ajá, a ver si alguien por ahí la tiene. Déjame. Mientras.
El
Adelante.
997
¿Sí?
58 57
Ujú.
97 85.
Sí. Vale.
A ver, antes de iniciar, Efraín,
Ajá.
pero ¿cómo le vas a hacer con la tableta? ¿Ya puedes?
Nada
O,
más. No, nada más sería cosa de escribir sobre ella, no, no es mucho problema eso.
pero espérame, entonces también déjame que hago cojo la tableta, ¿no?
Sí, ya ves, ya he escrito ahí.
Ah, ok, ya. Ah,
Sí.
exactamente, ya está, sí.
Mm.
No hay necesidad de más.
No. Uy,
Ok, sí, ahí está.
yo solo quiero borrar.
Sí
Ya
se
está.
borró, ¿eh?
Sí. Ajá, nada más déjame, ay, nada más déjame en la presentación. Mm, ahí está, ¿no? Entonces,
A ver, espérate, déjame nada más que entre bien porque se ve pixelada la imagen.
sí, cierto. ¿Por qué pasa eso?
Eh, no sé si se congeló. No nos llegó. Me imagino que quisiste compartir la presentación ya, ¿verdad?
Sí, sí.
A ver, ¿puedes mover el cursor? Creo que se congeló, ¿eh?
Estoy moviendo el cursor y sí, yo tampoco en la tablet veo nada.
El cursor sigue arriba de la T. No se
Ah,
mueve la manita.
sí, sí, espérame entonces. ¿Quién sabe qué pasó aquí? Voy a...
Ujú.
Ahí
Ok,
está, ya.
exactamente. Y ahora sí no tienes presentación. Ahí quedó.
Eh, Ajá, ok.
Muy bien. Bueno, pues Efraín, adelante. Todo tuyo. Cuando gustes.
Vale. Ahí está. How do we do this? In English, Spanish, German?
Como no hay michoacano, te la voy a aceptar en inglés.
All right.
O sea, hay michoacano.
Okay, there is no Michoacanos except for me, right? Yeah, straight out of C4. Okay, okay. So, are you going to do some sort of presentation of me, or?
Efraín, adelante.
Okay, so, hi everyone. I suppose that by now you know who I am. My talk is going to be concerned mainly with the concept of tensor product of vector spaces. Okay, but before we got into things, I'm going to try to motivate with a problem. I usually like to do that. All right. So, so to Euclid, it was known that the formula of the volume of a pyramid is given by that formula in there, right? So my first question will be, do you have any idea of how to prove this formula? Have you ever encountered a proof for that fact? Anyone? Okay. I'm, I'm going to assume no. So if that's the case, there is some annoying fact about the proof of to this formula, and that will be that all of the known proofs of this formula involve differential calculus, which is somehow counterintuitive if we think of it, because it's like, come on, to find, sorry. Come on, it's just as a pyramid is a simple polyhedra, so it should be easy to deduce an elementary proof for that fact. Turns out that's not the case. All of the known proofs involve some sort of infinitesimal procedure. So why is that? So the natural question will be, is it possible to find a proof to this formula without having to resort to differential calculus? That means if we can just somehow deform the pyramid so that we can get it into a known shape that we know how to calculate the volume of. Okay, so we know an answer to that question, and it comes, surprisingly enough, from linear algebra.
Okay.
Mm-hmm.
Now, so are there any questions from the students of what Efrain has told us about so far? Daniel, Salvador, any questions?
Yeah, exactly. For a moment, I thought I was speaking to myself.
No, I haven't any question.
Okay, fine. Okay, so yeah, as I told you, by the mid part of this talk, my aim is going to be to answer this question. So to that.
Okay, but wait,
Mm-hmm.
I mean, so Efrain has made a statement in the history of mathematics. So calculus, when it was discovered, in terms of the timeline, we have Euclid here and calculus around here, Newton, Leibniz.
Mm-hmm.
So think about it. Efrain, you can.
Yes, I'm going to proceed now. So for that, yeah, put a pin on that, and we are going to come back to it. Okay, so for now, we are going to enter to the core of my talk, that is tensor products of vector spaces. That at first seems like a long shot because it's like, why? But okay, later on we will see why. But for that, we are going to make some definitions. And for that, we consider K vector spaces over a field.
Mm-hmm.
And then a vector space W together with a K multilinear map phi is called a tensor product of these vector spaces if the following property holds. If for every vector space U and every K multilinear map psi, there exists exactly one endomorphism, exactly one linear map from W to U such that this diagram is commutative. Okay? That's the pair W phi is what we are going to call a tensor product of these vector spaces. That's just a definition. And this property is called the universal property of the tensor product. So that's the definition. I mean, more to it, there's nothing more to it. I mean, if you can think of it, it's like a tensor product, what it's doing is just is giving you a way to enclose all the multilinear maps from the Cartesian product to any vector space. Mm-hmm. That would.
Wait, so, but a tensor product of the VIs.
Yes, of course.
But I mean, okay, so I understand you can move, but what about W?
No, I mean, if you can find a pair, W phi.
Oh, a pair. Oh.
Exactly, it's a pair. Then this pair is what we call a tensor product of the vector spaces. Okay, so is that clear somehow?
Is this true for finite dimensional vector spaces or?
I'm not making any assumption on the dimension of the vector spaces, so they could be in principle infinite dimensional. Yeah, everything is fine. Okay, so that's a nice thing actually. Okay, so that's the definition of the tensor product of the VKs of the VIs. Then,
Can you?
yes.
I just want in that clear. So right, the tensor product of the VIs will be the pair W and U.
W and phi.
W and
Phi, the
VI.
multilinear map.
W and the linear map.
Yes.
Okay.
Yeah,
So,
U is any vector space, so you cannot fix that.
right. U will vary also the other two maps, right?
If for any multilinear map, for any multilinear map going from the Cartesian product to the vector space U, there is exactly one psi such that this diagram commutes. So this should be something of the sort of exist exactly one such that diagram commute. So exactly. So these guys are what we start with. And for some miraculous reason, you have another multilinear map, in another vector space. Then given this information, we know that there is going to be exactly one such that this diagram commutes. That's the definition. More, I'm not asking.
Thank you.
Okay. Okay. So now, the very valid questions does such a thing even exist? And if so, is it unique? Okay, so what do you think, guys? Okay, I feel like Dora the Explorer here. So yes, tensor products do exist, but they are not unique. That's kind of a bummer, but not so much, because even though they are not unique, there is a way to identify them. What do I mean by that? Okay, so the uniqueness of the tensor products will be like, if you have, again, the same hypothesis, K vector spaces over a field, and if we have another tensor product, and recall that a tensor product is a pair, then there is exactly one linear isomorphism between W and W tilde, such that this diagram commutes. So we say that tensor product is unique up to a unique linear isomorphism. That's quite a nice thing, actually, because it's like, okay, at the beginning you could say, oh, these things, there is no way they are going to be unique, and there is no, a priori, there is no way why should be related with one another, but turns out that it is. They are.
Now, coming back to Daniel's comment, what is the dimension of W if the VI?
I want to illustrate that with examples.
Okay.
Yeah. Well, of course, if any of the vector spaces is infinite dimensional, it makes sense that the thing it will be infinite dimensional as well, but we will come back to it. So yeah, normally, exactly. Normally, one realizes the dimension of the tensor product by constructing one such a vector space in a multilinear map phi, such that it satisfies the universal property. However, for the purpose of this talk, I don't see it necessary, because my goal is to introduce it and making clear that you have been using tensor products without realizing it for a long time. Okay, so for the moment, we are not going to worry about the construction of the tensor product. We are just going to assuming that it is possible to construct them. And then through examples, we are going to obtain some useful properties from them.
Now,
Okay.
can you go back? Yes. So there. No, one. Because I just wanted to use that blank space.
Yeah, sure.
So, Efrain, can you also tell us like how to construct? What is the analog of what you're saying? But given two vector spaces, the universal property for the direct sum. I mean, because we are more comfortable with the direct sum of a vector space and not so much with tensor products. Because you also have a universal property, right? For
I mean, yes, and it's essentially the same.
So can you write down the diagram there? So now given two vector spaces,
so we will have
vector spaces will be the direct sum, blah blah blah.
Wait a second.
Yes, thank you.
Okay. So
but wait, we are not seeing anything. I see you writing, but we don't see nothing on the screen.
Yeah, I know, because
okay.
So we have V1 and V2, and then we will have, I mean, you know how the direct sum is defined, right? So then we will have that V1. It is exactly the same thing, actually. V1 times V2, and then for every vector space U, we will have exactly one map making this guy commute. But I mean, it's exactly the same. I don't know what. I don't know what do you want me to say.
So so for the students, I just want you, so we have encountered how to define the direct sum, and we do it like not a formula but directly.
Yes.
But what Efrain presented here for the tensor product, it is a different approach. You can define the tensor product in the same way that we define the exterior algebra. But he's taking a different approach, which is very useful. And I mean, that's why I asked him to write down in his approach how is the direct sum of two vector spaces is defined in terms of this. So you start with V1, V2. He wrote V1 direct sum V2, but actually that should be a W. W is the direct sum if something like that happens with the linear maps. And then there's a uniqueness up to linear isomorphism, and that's what we have V1 plus V2. If you feel that this is a very complicated approach to describe something that you know more easily to describe, that's correct. But this new approach will give you a broader sense of some abstract mathematics that is very useful. So sorry for that, Efrain.
No, but you're very welcome, because exactly that's, I actually omitted defining the exterior algebra because I assume I'm going to run out of time, but yes, I wanted to introduce that and the symmetric powers, but we will see. Yes. Okay, so exactly. Universal properties are a very useful thing. That's what Andres is trying to say, and yes. So as soon as you can learn it, the sooner you can learn it, the better. Okay, yes. And exactly, that's going also in the same vein as Andres' comment. And it said that, yep, the tensor constructing explicitly what a tensor product is, or a tensor product. Yeah, it could be useful from a set theoretic point of view, but in reality, I don't know anyone who uses that such a construction. What we do in practice is that, just as the direct sums, we use something, some familiar vector space that satisfies the universal property of the tensor product, and then because of this uniqueness up to linear isomorphisms, we know that that will be good enough. And that's why that's why I claim that we already know what, or at least we have make use of some tensor products in real life, if you want to say that. So yeah, no one worries about the construction, and that's why I omitted it. But if you are really, really interested in that, we use the notion of free vector spaces. If you are good in algebra, maybe you encounter this concept. If not, don't worry. Okay, so yeah, all of this time I've been talking about the tensor product, even though it is not unique. But yeah, because that's customary to do. And we denote the space W by this strange symbol, and the corresponding K-linear map phi is denoted by this guy. And instead of writing the usual notation of the map, we will just write V1 tensor blah 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 tensor VK for any VIs in the corresponding VIs, right? That's just notation. So right. So we could say that we are now familiar with tensor products. So fine. Then another very valid question would be, given the particular case of three vector spaces, what is the relation, if any, between the spaces V tensor U, W tensor U considered as a one vector space, and the other way to put parentheses on it? So what do you guys think will be is there any relation between them whatsoever? There is no wrong question, just please don't let me talk to myself. Or do you? I don't care. Okay, so I'm assuming that your naive thought it will be that, yeah, because it's a product, it's reasonable to consider it to be associative. And in fact, that's the case. The tensor product is associative, and we need to be very careful about that. What we mean by associative is actually the following. It seems like a mess, but it's quite easy to understand, actually, if you think a little bit about it. So we do it in the totally general case, and then we go back to the three vector spaces situation. So what we have is we have a collection of vector spaces. Then it can be proven that there exists a unique linear isomorphisms A such that the following diagram commutes. So we have A such that this diagram commutes. So we have the Cartesian product of the vector spaces. That's like the basis of the tensor product. And then we have the multilinear map psi, phi, or in this case, tensor. And then the claim is that there exists exactly one A such that this diagram commutes. Do you remember that this is just this tree is exactly the universal property of the tensor product? And this is just the way of saying that it doesn't matter how do you put the parentheses around the things, it's going to be the same. Is this diagram clear? I mean,
I have one question.
yes.
What does the parenthesis notation means? I don't quite get.
Which one? This one?
No. For each vector space, there is a parenthesis 1, parenthesis L.
Yeah, it's just a collection of things because you have from 1 to K1, and there is just a way to enumerate them. And I want to say how to put the parentheses around the thing. It means nothing. It's just a way to count them.
All right. Yeah. Okay. Thanks.
Okay. So, any more questions? Right. So that's the associative property of the tensor product. I mean, that's precise, mathematically precise way to say it. And then exactly returning to the situation of the three vector spaces, then we will have that if for any way of putting parentheses around the things, there is going to be an isomorphism. And then composing the respective isomorphisms, then we just say that we omit that and we just say that the thing is the same. Hence, the claim that the tensor product is associative. We have that. And yeah, even though knowing that for the situation for three vector spaces is nice and everything, the true power of associativity is that it allows us to restrict ourselves to the much more easier case in which we only have two vector spaces. Why is that? Because the general tensor product is isomorphic to this guy. This is a humongous vector space, but it still is just one vector space instead of the whole bunch we already have. Implicitly, you have to do it, but at least for psychological reasons, it's easier to do so. So, all right, so from now, so we have that, and then restricting to the case in which we only have two vector spaces is nice. Then, now, again, because we are talking of a product, we would like to know, what about commutativity? Does it hold? Yes, so I'm going to save me the 10 seconds. Yes, it is. It is. The precise way to state this is something with diagrams, so I'm going to omit it for the time being. It's enough to know that there is an isomorphism between V tensor W and W tensor V. All right. Okay, so for the properties of the tensor product, again, I'm going to omit the precise statements. So if we have a non-empty set of indices and we have a family of vector spaces, then we have what you call it, a distributive property. You just, yeah, I don't know what else to say. Then not okay. Then not the nice case in which one of the vector spaces is zero. Then tensoring with any vector space gives you again the zero vector space. So that's nice. Also, if you consider one of the vector spaces to be the field itself, when you tensor it with the vector space, is isomorphic to the vector space itself. Then in general, for any n, we have the following isomorphism. We have kn tensor v is isomorphic to the direct sum. So my question will be, if anyone is in the mood, how would you prove this claim from these claims over here? It's a one-line thing. So how will you do that? Anyone? Well, you could do that as an exercise. I don't know.
Wait. Give them a couple of minutes.
Okay, yeah, because it's very awkward because it's like, yeah.
You can make it pairwise, like splitting the product of Kn and then using the property you have right before,
This one, right?
right? And then the first one.
Exactly. That's the proof. Yeah. Use the distributive law and then use this property and that's it. Perfect. Fine. Okay. So now,
Sorry, can you
yes.
go back? I just want to see. Okay. Yes.
Yes. Mhm. I mean, I could possibly have making a mistake somehow somewhere because I did this in one day. So if so, just let
No,
me know.
I just wanted to take advantage of what you have here, and like, because you like abstract things. So the set of all k-dimensional vector space becomes a semigroup or a ring under the tensor product.
Well, yes, could be. Yes. No, but actually, I mean, I think about that, but then in the meantime, I'm going to ask some question. From these properties over here, do you have any conjecture on what the dimension of the tensor product will be in the case all the vector spaces are finite dimensional? No?
Like the sum of the dimension.
If that will be the case, then this will have dimension of v plus 1, no? But we are saying that this is isomorphic to v.
Well, in the meantime, so what I wanted to stress is, if you look at the collection of all of the k vector spaces, I don't know if we should limit to finite dimensional or not, then you have an operation which is the tensor product. And you can think of that as a product
And then the
with a
direct
unit, which is the field itself. You have no invertible element. Well, it's not a ring because you cannot invert.
Yes, you don't have, well, yes. No, exactly, yeah. There is no v minus 1, sorry.
Yeah. But I mean, because using this fact of vector bundles, Efraim, is how you come up with K-theory.
Okay, I don't know much about K-theory. Actually, I don't know anything.
So,
But,
no, but I mean, so you have the family of all vector spaces, but they are vector bundles. You do the tensor product, but there are no inverses.
so you don't have any unities.
So you have to come up with some additional structure to have an multiplicative inverse, and that will give rise to K-theory. The base of the vector bundle doesn't change, X, and you have all the possible vector bundles, and that's the K-theory of X.
Actually, I think I attended some years ago a course on Keller geometry, and we did something like that. Yeah. I don't remember if we used characteristic classes, but yeah.
Oh, yeah, you do.
Okay. Yeah. So, that's fine that I remember because my advisor is probably going to see this video. So, and it was his class. Yeah. Okay. So fine. So exactly. So again, conjectures on the dimension. We know that the sum cannot be, and actually that would be very bad because we know that 0 tensor v is equal to 0, and the dimension of v is at least 1. Yes, at least, yeah. So anyone else, or again?
Probably the product then.
Yes, exactly. If it's not one, it's the other one. Yes. Yeah, actually, yeah, that's a nice, I mean, a naive approach, but normally it works. Yes, the product. Okay, but we are going to enter into details a little bit further on. Okay, yeah. For the time being, so what we have is we are going to define the so-called Kronecker product of linear maps. For that, we have a linear map between two vector spaces, and we define the Kronecker product of the maps as this map defined on the tensor product of the V's with target the tensor product of the W's, and the definition is pretty straightforward. Just take any tensor The elements of the tensor product are called tensors, no surprises there. And you just send it to the tensor of each of the images. That's what it's called, the Kronecker product. So we have that. Yes, the Kronecker product satisfies all the nice properties we have, we want. So what I mean is, for example, we have, oh, come on.
Sorry, Ryan, can you move back? Because so here you are also making the notation of the elements of the tensor product, right?
Yes.
I think the first time that me1.
No, actually it's not. I way back.
On the new ones?
Here, you see?
Oh, right. Oh, sorry, I didn't remember. Right, yes.
Yeah. I mean, yeah. So no, it's not. It's actually no. But what I mentioned for the first time is that the elements of the tensor product are called tensor, but not this notation we already encountered.
I missed that. Thank you.
Yeah. Okay, so again, so we went with the Kronecker product, something like that. And exactly, what do I mean by expected arithmetic relations? For example, if we have phi1 tensor, the identity map on V2, then what this thing will be. No, what I'm saying here. Sorry, I got confused. No. What I'm trying to say here is that given, for example, phi alpha 1 plus beta phi 2 tensor phi 3, then this will be what? Come on. Alpha phi 1 tensor phi 3 plus beta phi 2 tensor phi 3. That's what I mean by that's what I mean by expected arithmetic relations. No? Okay. That was just a parenthesis.
I have a question. In the case when the linear functions are, for instance, an isomorphism, does it hold that the tensor product is also an isomorphism?
I mean, I want to say no, but I'm not sure. Andres, help me. I want to, oh yes, I think so. Yes, the inverse being just the product of the inverse. Oh, Dios. The inverse being only tensor phi 2 inverse is just the product. It's just the inverse of the product. Yeah. Yeah, sure. But both need to be an isomorphism. Otherwise, you could not claim this.
But I think that if we only ask for surjective or injective maps, then the tensor product will also be surjective or injective, right?
Let me think a little bit about that. No, I don't think that's the case. No, no, exactly. No, because if, for example, for example, the easiest case, if you only consider the identity V1 tensor phi 2, why should this map be injective or surjective for general phi2. There is no obvious reason why we should believe that. No.
Yes, but I think Daniel was saying if both of them are surjective.
Yeah.
Eh,
Because I was thinking that you can use the matrix representation, and I think the tensor product has also a matrix representation, and then you can use like the rank of the matrix.
yes. No.
But
Yeah,
I'm not sure.
exactly. If all of the maps have the same algebraic properties, then I assume the tensor product will inherit it as well. Yeah. I mean, don't quote me on that, but yeah, I mean, I don't see any reason why not.
Yeah, I think maybe the only thing is the detail might be if the characteristic of the field must be 0. If you have positive characteristic, I think you might run into trouble.
Because at some point you have to divide for some number. Yeah.
I think that, but in characteristic 0, you are fine for sure.
Yeah, because I see, because we normally calculate we calculate the Taylor series of the map, and then we divide by numbers, something of the sort. Yeah. Now, exactly. Yeah, but yeah, exactly. If the field has characteristic 0, then all the properties of each of the factors should be inherited into the tensor product. Yes. Okay. So now, if we have the map, then we have this map, which is clearly is multilinear. Then the definition of the universal property of the tensor product implies that there exists exactly one unique linear map, iota, such that the following diagram commutes. That's just the universal property of the tensor product, right? So, okay, so it can be shown that iota is an injective map, and in the case in which all of the vector spaces are finite dimensional, iota is in fact an isomorphism. So, yeah, that's quite nice as well, because it means that in the case that all of the vector spaces are finite dimensional, you can treat Hom like an homomorphism and distribute it along all the factors. I don't know if I'm making sense. So with that, we get an injection, which is from the tensor product of the dual of the vector spaces into the dual of the tensor product. Why is this a consequence of this fact? Can anyone just tell me the proof? It's again a one-liner.
Maybe if you can go back so that we will know.
Yeah, sure.
Thank you. So V star can be identified with home of something. So you can take the W's to be K for all of the W's.
Then in that case, we will have K. And we will have the tensor product
of K,
which we saw that was isomorphic to K, right? Right, that will be the proof to get this injection and isomorphisms in the finite dimensional case. Fine. Why? We already saw that. Then exactly, one of the classical results concerning tensor products is the following in the case of two vector spaces, which is, I'm sorry, I need to erase my writing. So given two vector spaces, there is this map going from the dual tensor W to the linear maps of V to W is an injection, is injective. And if any one of the V or W have finite dimension, then this map is in fact an isomorphism. So yeah, this is what I've been saying all along, that we have been inadvertently using tensor products since a long time ago, because you encountered this guy in second semester in linear algebra 1, right? So yeah, that's a very nice property. And then exactly, this is like further confirmation of the conjecture we already have, because the dual of a vector space has the same dimension as the vector space itself. So the dimension of this guy is going to be, in the finite dimensional case, right? The product of the dimensions, because we know that that's the dimension of this vector space, right? So that's like an easy proof without resorting to the construction of the tensor product itself, which is quite cumbersome, if you ask me.
And actually for W equals the field, that's the definition, right?
For W, what do you mean?
If W is K.
Yeah, exactly. Yeah, that's just the definition. Yeah, exactly. That would be an isomorphism between between dual tensor K, which is again the dual, and the dual itself. That's the definition of the dual map, of the dual vector space. Yes.
Even in the infinite dimensional case.
In that case, yes. But that's because one of the vector spaces is finite dimensional, in this case W, which is K, which is what this proposition warrants. It's just enough that one of these guys is finite dimensional for the thing to be an isomorphism. So fine. Yes. Okay, yeah. So okay, so you could be very validly asking, what the hell was that? Yeah. Oh, now we are going back to the original question. We are going to talk about pyramids. Okay. So, and it even has a fancy name and everything. So because it's sort of a big deal. I mean, not quite. The proof is just a one-liner again. But okay, so we know that given any two polygons A and B of the same area, then it is known that A can be cut by finitely many straight cuts. What I mean is that, well, I'm going to show that in the picture, into pieces from which one can make B. And this thing has a name. This is the Wallace-Boljager-Wien theorem. And in pictures, it looks like this, basically. So you take any polygon, there is a way of making on it straight cuts, like this, such that it can be deformed into any other polygon we want, in this case, the square. That is known for the two-dimensional case, and it's a theorem. Cheers. Okay, so again, we are going like making just the natural questions. In 1900, it was on the second Congress of Mathematicians or something in Paris, if I recall correctly. Hilbert asked whether this is true for polyhedra of the same volume in 3 dimensions. In particular, he asked if it's true for a cube and a regular tetrahedron. That means that if there is a way to perform an analogous of this guy, and this being the pyramid, there is a way of cutting it in a finite set of pieces by means of straight cuts, such that this cut can be rearranged to make a cube. So, what do you think? I mean, normally we've been right about our intuition. So what do you think? Is this possible?
Yes.
Okay. Anyone else?
So I have not looked, but can you say something? What was the approach for this result? They used some analysis, or it was geometry, or
No, we use tensor products.
for that one there?
No, for this proof here.
Yes, yes.
Yeah. Honestly, I don't recall. I just I just copied from the book. I took the talk, but I
Yeah.
don't really recall. But I mean, it was. I mean, it cannot be too difficult, right?
But this is prior to 1900s.
I mean, Gauss knew about this thing, and that's actually Gauss was in one of his letters to one of his colleagues. I was asking, "Oh, why can't we do that for polygons? But how is it that we cannot find a proof for a pyramid and a cube?" Oops, sorry, I spoiled that. So if Gauss could find a proof, then yeah.
But I mean, okay, because you are only focusing on polygons.
Exactly, of the same area. Of course, that's should be given. Yeah.
If I don't recall wrong, you use like triangulations, and then you use the fact that a triangle can be transformed to a rectangle and a rectangle to a square, and that's how they prove this theorem, I guess.
Mhm.
Right,
Yeah.
right. So maybe that's the whole idea. Just for any polygon, go to the square.
Right.
Yeah, I mean I think that's a common ground. Just go to the square and then deform it into the anyone you want, because you know you can reverse the thing.
Exactly. Right.
Yeah.
Right.
Okay, so that is known. So the bets are done. Yes, why not? It should be possible for the tetrahedron. Well, okay, we are going to be thoroughly disappointed. And for that, yeah, we in order to answer this question, we first define the so-called then invariant of a polyhedron. What the hell is that? Okay, so given a polyhedron A, we define its then invariant in this as dA, defining this vector in this tensor product of Q vector spaces. Quick parenthesis. What's the dimension of R as a Q vector space? Just for fun, because it's not really necessary, but just for fun.
So, right, you think about Ricardo's class on Galois theory.
Okay, I was just thinking about the square root of 2 actually, not nothing fancy. So anyone?
Should be like the degree of extension.
What do you mean by that? I mean, Q squared of something cannot be R because it's not. So could you elaborate a bit more, if you don't mind?
I was thinking, bro.
Yeah, sure. I mean, that's how math works. Well, I'm just going to say, and then you think about it a little more. R is an infinite dimensional Q vector space. Why? Okay, homework. So now we define the then invariant of the polyhedron given like this.
Wait. What about the second one? R mod Q.
Yeah. What about it? Yeah.
The same question did I mention?
Yeah. No, sure. But I thought you were asking the students.
Oh, come on, you can tell us now. You already said the dimension for R, and what about R mod Q?
Uh-huh. I mean, it's just the equivalent classes. But that should be infinite as well.
I think I don't know. I suspect that it is also infinite.
Yeah.
Yes.
Ah, okay. Yeah, Andres. I was trying to write a proof in my head. Yeah, I think it's infinite. But I mean, again, don't quote me on that, but I think it's infinite.
Now LE.
For example, yeah, because you are just identifying the rationals. I mean, you have a uncountable number of things there. So, and you have square root of 2. The class of a square root of 2 is non-trivial. How do you write that as a sum of equivalent classes?
Yes. Yeah, that's right. No, but
Okay.
I'm trying to understand still RQ with your alpha E.
Yeah. I was trying to describe what the then invariant is. So we have this guy defined like this, where the sum runs over the edges of the polyhedron, and alpha, L of E, is the length of the edge, and alpha is the angle at the edge. What do I mean by that? What do I mean? Like, we have the polygon. I don't know. We have E1, E2, and then we have that. This will be alpha of E1, no? We have, just think of, I don't know, yeah. Just think of a cube. You just have, oops, I don't see. No, you just have this guy, this edge over here, and this edge, and then we will have the angle at this guy will be just draw an imaginary line here, and going all the way down to the face, and then this angle will be the angle at the angle alpha at this edge. Am I making sense? So you have the, I don't know, I'm not very good at drawing.
So
Yeah, the angle that the faces make, right?
Yes, but not at the vertices. That's important. Just anywhere to want on the polyhedron, except at the vertices, because that's a mess there. But yeah, the angle the faces make, yeah, that's a way of looking at it. I mean, yeah, the faces divided by the edge E.
So for a cube, you get 0.
The then invariant of the cube.
Yeah.
Yes, it is 0, but you're getting too ahead.
I have to understand because I don't know this.
Yeah. Okay, yeah, exactly. And exactly, it's 0, and we're going to see in a moment why. And that's the key of the proof, actually. Yeah. Now, because the tensor product is linear, we saw that. We know that if we cut the polyhedron A into 2 pieces by a straight cut, then the then invariant of the polyhedron is going to be the sum of the then invariant of each of the parts. Why is that? Imagine that you cut the cube like this, and then you will have these 2 polygons, right? Then each of the around the cut, the edge is going to be split into 2 or whatever part, yeah, by a straight cut, into 2 parts, and the angles as well. So when you add it together, because of linearity of the tensor product, you are going to get the same thing you had before, because you are going either have a cut of the length or a cut of the angles. But when you add it together, you get the same thing. So by induction, you get that if we cut A into R parts by straight cuts, then you're going to get that the then invariant is just the sum of these of the then invariants of the parts. So we have this, and with that, we know that. We conclude that if we have two polyhedron of the same volume, and if we know if they can be cut from into each other by straight cuts, then they are going to have the same then invariant. Do you see this? Because if you have one cut by straight cuts, then you know that the then invariant is going to be preserved by these cuts, and then you put it into the other guy. But because it's consistent on the same cut part, then the then invariant is going to be the same. Is this clear somehow?
Yes.
Yes. Okay. Okay, that's a necessity, but it's not an if and only if, of course. But that's enough for our purposes. Why? Well, Andres had rightly observed. We calculated the then invariant of the cube of volume L0 cube, just to give it a name, no? And exactly, we know that at each edge, we know that the angle is half pi, no? And rightly so. Then we have that the then invariant, because the length of the edge is equal. So then we know that the then invariant of the cube is just 12 times L0 times the equivalent class of 1/2, because you divide by half pi by pi, which because we identify every rational with 0, then you know that the then invariant of the cube is 0. Yes. So now we consider the tetrahedron of the same volume. We don't use the volume anymore, but just to be consistent, and whose length of edge is equal to L1, just to give it a name. Then now the question will be, what the hell is the angle between any two faces? Because it's a regular tetrahedron, it's going to be the same, no? Then this is the situation, no? We have the tetrahedron, and we want to determine this angle between this face and this face, which, because of regularity, it's going to be the same at any face we choose, any pair of faces we choose, right? So yeah, we have this, and we have that the center of the triangle at the base, the triangle ACB, so we have that the height of this triangle, which is given by AE, we know that the center of the we know that the center of the triangle splits the height in a proportion 1 to 2. That's usual elementary geometry, so you should be able to do that if you don't see it. So, and because of regularity, so we have that the segment AE has the same length as the segment DE. DE, AE. Then we will have that the cosine of the angle alpha is just the definition of the cosine, the length of the segment ME divided by the length of the segment DE. Yeah, definition of cosine. And because all of these relations, so we have this, and then we obtain that, therefore, that the cosine of the angle is 1/3. Are all we in agreement here? I'm going to assume yes. So now, with this, we get the then invariant of the tetrahedron, no? Which is, again, because of regularity, all of the angles and all of the edges have the same length. So the tetrahedron, the then invariant of the tetrahedron is given by this quantity here. So what about that? Yeah, we claim now that this number here, as horrible as it seems, is not irrational. So how do we do that? As usual, assuming the opposite, assuming that beta is rational. So say that beta is of this form with q some non-zero integer, right? Then we will have that 1/3 is cosine of the cosine of r times pi. No? That's just by definition. I mean, by what this guy satisfies. So now we do a little bit of algebra, but I'm sure you're fine with this. We know that 2/3 is not an algebraic integer. Just as a reminder, an algebraic integer is a root of a monic polynomial with integer coefficients. No? And we know that the only, because of the definition, that the only rationals that are algebraic integers as well are precisely the integers. And because 2/3 is not an integer, so we know that 2/3 cannot be an algebraic integer, right? I mean, yeah, fine. Now, if we consider, however, z to be e to the ir pi, then we will get that c to the 2q is equal to the c conjugated to the 2q, which is equal to 1, no? This will mean that c and the conjugated of c are both algebraic integers because both are roots of the polynomial x to the 2q minus 1. We just verified this. And here we have a problem. Why is that? Because the algebraic integers are close on their addition, so we will have that the sum of these two guys is again an algebraic integer, but we know that these guys add up to 2 times cosinus of r pi, which we saw by assumption that that was equal to 2/3, which is a contradiction. So the problem is assuming that this guy is rational. And then we prove that beta is irrational. Is this clear?
Yes.
Yes, okay, fine. And then, oh, hooray. So we know that this is enough to answer Hilbert's question in the negative. So against our intuition, because honestly, I also thought it should be possible, but no, because the then invariant of the tetrahedron is not 0. And we just saw that the then invariant of the cube is equal to 0. So because they have different then invariant, then we know that they cannot be deformed into the other by straight cuts, which is a bummer, because this also implies that there is no elementary proof for the area of the volume of a pyramid, because by elementary we only wanted a finite number of cuts to perform a finite number of cuts on the pyramid so that we can deform it into something we already know the volume of. But we know that that is not possible, because if that would be possible, then reversing this process, we will take this strange tetrahedron, polyhedron into the cube. But we know that this is impossible. So yeah, and no, it doesn't matter how hard you try. If you aim to find the volume of a pyramid, you have to use the formula, and to prove that, you need to resort to infinitesimal methods, which is strange, but so it's life. Are there any questions so far? Fine. Yeah, but that was just an application of tensor products. But yeah, this is the differential geometry lecture after all. So let's do some geometry, shall we? Okay. So to do that, yeah, this is a completely different topic. I mean, that was just a funny application. No? So for that, we take an n smooth manifold, smooth n manifold, and we consider its tangent bundle. No. Then we define for any pair of natural number Rs, we define this set over here. And exactly, using that, and exactly, it can be shown that this guy.
Can you go back just there, just so that
on this guy, there is a unique smooth structure making this guy into a smooth vector bundle. Yeah.
Yeah, just put it there. So can you go back to the previous slide, please? So remember, if we put R equals to 1, S equals to 0, we have the tangent bundle that we already defined before for R equals 1 and S 0. And also the other way around, if R is 0 and S is 1, we have the cotangent bundle. So what Efrain here is doing is something more general that includes both cases, the tangent and cotangent bundle. Right, thank you.
Yes, okay, so you just got 2 slides ahead. But anyway, so exactly, so that can be proven. No, now my question will be, what's W? What's exactly the typical fiber of this bundle? Can anyone tell me? Because it can be explicitly known. So again, in the case, exactly, we know that in the, we know that in the case R equal to, for the love of God, we know that in the case R equal to 1, we know that W is equal to Rn, right? And for the X equal to 0. And for the case, yeah. So, and for the case R equal to 0, S equal to 1, we know that W is the dual of Rn. So what will be for general cases? Rs in N arbitrary, then we will have that W is equal to
Like a product of Rn.
How many times?
Rs times.
Yes, exactly. Rs of Rn, which is equal to the R-fold tensor product of Rn tensor with the S-fold tensor product of Rn of the dual of them. No, exactly. That's the typical fiber. Fine. So that's it. And exactly, just in the same, just repeating the comment Andres already did. Well, no. So for that, because this is the tensor bundle, that's how is it called, is a smooth vector bundle, then it makes sense to talk about the sections of this vector bundle. And this set of sections, this vector space of sections, is called this the set of tensor fields on M. Tensor fields of type Rs. No, it's not R choose S, it's Rs. Okay, now, exactly, that's the comment Andres already did. The tensor bundle can be seen as generalizations of some familiar vector bundles. And indeed, T10 of M is the tangent bundle, T01 is the cotangent bundle, and T11, because we already have the isomorphism V star tensor V W equal to hom of VW, then makes sense that TM tensor TM is just the bundle of endomorphisms, which I'm not sure if you already saw, but I mean, makes sense.
No, so we have only seen the tangent bundle,
The cotangent.
the cotangent bundle, and also the exterior algebra.
Okay. Yeah, if I have some time left, I can talk about that. But yeah. But okay, so you just put a question mark on there. Yeah. But yes. Yeah, exactly. As Andres perfectly said, the tensor bundle is just a generalization of the bundle you already know. Also, given a vector field on M, we know that the differential of the flow is an isomorphism. No, that I'm sure you already saw this theorem. We know that for any integral curve C of X, the differential is this differential is an isomorphism. No, which again, the dual of this differential, it's going to be M is finite dimensional, so it makes sense to define the dual. Then we also have an isomorphism of the dual tangent spaces. No. Now we have this differential and we have its dual. And then we have, because we have the theory of Kronecker products, we can define the Kronecker products of these maps and obtain an isomorphism, which I am going to denote by this symbol between the tensors of type Rs. No, I mean, it's just a Kronecker product we already encountered. You just take phi. This is going to be R times d phi dx at the point Cxt naught times the S-fold of the dual, no? X C X T naught. No? The Kronecker product we encountered before. So we have that. What else? Yes. Okay, so, and also, you already defined the idea of Lie derivative, no? In terms of the flow. Exactly the same thing can be said about tensor fields, the sections of the tensor bundle. Just make this definition. The Lie derivative of the tensor field at the point P in M is defined as this map applied to the tensor field at the point Cxt with, again, Cx, an integral curve of the vector field X, starting, that's the way we say it, at P. No, that's a definition. Yes. We have that. And then, exactly, because we know that the flow is a one parameter subgroup of the group of diffeomorphisms, we know that we have a very nice property of the of higher order Lie derivatives. What exactly is that, the relationship? We have that for any k, any natural number k, we know that the kth Lie derivative of the vector field in the direction of the vector field x of the tensor field alpha at the point P is just given by the kth derivative at 0 of this guy. And the proof is a very straightforward proof by induction, which we do now, because seriously, there is nothing behind it. So the case k equal to 1 is just the definition, right? I mean, so that takes care of the base case of the induction proof. So the k plus 1 Lie derivative is just by definition the kth Lie derivative along the vector field x of the Lie derivative x of the Lie derivative up on the direction of x to the tensor field alpha. So we just use the induction hypothesis in the definition of the Lie derivative, and then we know exactly. We commute the derivative in this map, and because this is one parameter subgroup, so we know that the composition is given by this guy. So that's going to be that, and then just as an element, you just change the variable, just name s equal to t, and that's it. And that concludes the proof by induction. Seriously, there is nothing more to it. And this implies that we have a curve, the formal Taylor series of the curve in TPM of RS of TPM, given by this, sending the real number t to this guy, which again lies in T, lies in the tensors of Commission PM. Then we know that at t equal to 0, we have the following formal Taylor series, because we have, by definition, this is just 1 over k factorial, the kth derivative at 0 of phi minus t of alpha tx of t. And we just saw that this was exactly this guy here, no? And it can be proved that in the case that x is real analytic, what with this I mean that each of the coordinate functions I is of class omega. That means that it can be expanded in a power series, and this power series is convergent to the coordinates, because you know that there are power series that do not converge to the series they are representing. You know that, right? You have the usual typical example. You have that this guy has Taylor series equal to 0, which obviously is not the same that this map. That's what I mean by analytic. So it can be proved. Actually, my PhD thesis is concerned with this kind of expansions. That's why I'm trying to push this really hard anywhere I can. So yeah, I proved that if the coordinates of this vector field are analytic, then the whole series is going to converge to this guy, and we have a converging power series.
So you have a fixed vector field x, and then you took an integral curve, that's alpha, right?
An integral curve of x.
Yes. So so you are defining the power series of x, basically, right? I'm sorry, the Taylor series of the vector field.
Of this curve.
Of the curve
of the curve that
Oh,
maps
okay.
t.
Along the curve.
Yeah, it's a Taylor series in one variable. That's the nice thing. Yeah.
Well, yes, for the students, the nice thing that I was going to say is that even though it is in one variable, because there is t to the k, something that the students can appreciate is that the expression that Efrain has here, it doesn't involve a chart or a coordinate system. It is independent. So that's something very nice about it. Usually when we have defined all of this, we do it by some coordinate system, something that we don't have here. So that's the nice feature of this formula. Now, the other thing that is not clear to me, this approximation, so it is on the entire curve or just a part of the curve?
No, it is exactly. It's a formal power series. That's why I don't write equal, because we don't know if the series converge even.
Okay.
Yeah. So it's what formally it's given by that. If for some miraculous reason, and in this case, if the vector field X is analytic, then the power series is going to converge, and it's going to converge to this guy.
But all right, and it will be because only one parameter t. But I mean, it's still it's just in the neighborhood of the curve, not in all of the curve.
Not in principle. No, exactly. It's just as both sides coincide as usual, as these statements usually go.
Right.
Whenever either side coincides, whenever the either sides are defined, they coincide.
It will coincide.
Mhm.
Right.
Yeah, exactly. And as I mentioned, this is just self-promotion because my thesis is infested with this kind of results. So that's why I'm pushing it really hard everywhere.
And everything is any manifold the only restriction you want an analytic vector field?
Exactly.
No other conditions. Okay.
Nope. That's the nice part.
Thank you.
So is there any more questions? No. Exactly. Yeah. And usually, exactly. Normally, this is why the expression that the flow is the exponential of the Lie derivative is justified. But I mean, this is a big abuse of notation because it's not even the flow; it's the Kronecker product of the differential of the flow. But that's how the mathematicians are, no? So that's a nice feature, in my opinion. Because normally you have the Lie derivative being the derivative of the flow. But a priori there, why should there be an inverse relation? But it turns out that there is.
Right. So before moving on, I think you ended up here. So thank you very much.
I ended up, well, yes, I ended up here because I don't know if you mentioned the frame bundle, because exactly because did you mention it?
No. I mean, that's why I asked you first. That was
Okay.
the only direction that I can work on because we saw the tangent bundle. So it was relatively easy to move to the frame bundle, but we didn't see the frame bundle.
Okay, yeah, no, then forget. Yeah, then that's everything I want to say. If anything, maybe something worth mentioning is that another nice application of tensor products is that we have. It's going to take me like 2 minutes. If we have for power series in general, if we have F, what's going on here? F, come on, I'm going to omit this. Rn to R, no? Then we have, how will be the power series expansion of F? We know that that is multi-indices alpha, 1 over alpha factorial of the alpha of F at 0, x to the alpha. I'm assuming you're familiar with multi-index notation, which is just equal to 1, the sum, k greater or equal than 0 of the sum over the multi-indices of order k, and then we have 1 over alpha dkf 0 of x to the alpha. And this we call, I don't know, fk, no? Of 0, of fk of x, no? These are all polynomials. So we know that f of x is equal to k greater or equal than 0, 1 over k factorial fk of x, which, and we define f, k, which is just as line, no, we don't say, oh, no, forget about it. We didn't define the symmetric powers. Yeah, I forgot that. Yeah, sorry, I wasted your time on that. Yeah. I'm so used to these things that I forgot. No, but no, I didn't define the symmetric power, so it doesn't matter. But yeah, what I wanted to say is that we've been working with tensor products from a long time ago. You just weren't told that that was the name of the thing, but yeah, they are a very nice tool to have. So that, I guess that was all I wanted to say. But yes, are there any questions or comments?
So first of all, so thank you very much for your talk.
Yeah.
I don't know if there are questions. Let's wait. In the meantime, I don't know if you said it. So the answer to Hilbert's problem, who solved it? I don't know if you.
It's a student. He's a student. Then.
Oh, then actually was the one.
Yeah,
Okay.
exactly. This one of the 23 problems of Hilbert, right? So Hilbert was in Paris. I think that's a funny story. And saying, "Oh, this problem is interesting." And when he came back to Germany, the guy already solved it. So yeah. So
And
it
then,
was part of the list very, very early.
So the counter example was given by then, and he was also Hilbert's student.
Yeah, yeah, exactly. And actually, this problem was his PhD thesis. Because back then it was very rudimentary the way he did it. But yeah, in modern notation, we saw that we solved it. But yeah, this problem was basically his PhD thesis. Yeah.
Because there is also another interesting, not invariant, but technique, the then twist.
Yeah, that's in topology, no?
Yes, exactly.
Yeah.
So I thought that was his work.
Yeah, I mean, could be, but I mean, now that well, I mean, of course you know that, but is it related to what I just defined? Because maybe there is an intricate way to define to.
I don't see it.
Okay.
I don't see that relation between the then twist and this then invariant.
Yeah. Yeah, but yeah, as I said, he was a student from Hilbert. Trying to mix German into them.
But wait, again, let's make sense out of this. I mean, Hilbert went to Paris to the ICM. I don't know if whatever happens then happens now. he gives his talk, and then after you give a talk, they will ask you to write down something and submit it.
Yes.
But then if he already knew that that problem was solved, but still it was included on the...
That's something that baffled me, because it's like, I mean, he was your student, so you should know what he's up to,
Yeah.
no? So, but no, apparently he didn't, because exactly he published it, and like literally like one maximal 1 year later, the proof was already
Exactly.
published. Mhm.
I think maybe Dan's work, it would be a year later or so, not...
Not immediately, right?
Yeah,
Yeah,
no,
yeah, I
no.
exaggerated that for the sake of the narrative.
Exactly.
Mm,
I don't know.
yeah.
Great. Are there any more questions or comments? Go ahead. Also, but it is a video from... But what is this video, Daniel, about?
The
The
Denver,
number five video. Mhm.
yes,
About then what?
About the
variant.
Silverster problem.
Okay.
But yeah,
They,
and if I yeah, sorry.
no, just they elaborate on the history of the problem too
Hmm.
in the video.
Mhm. Yeah, yeah, but
Do you know
exactly.
if there is like an equivalent or an analogous invariant in higher dimensions, or is still an open question?
You no, exactly, as maybe actually it's also mentioned in that video you are referring to. Exactly, the higher the dimension, the more invariants appear. So yeah, the conjecture is that no, there are no higher polyhedron that are scissor equivalent. That's the name, I think. I mean, you cannot make straight cuts and deform it into the other, because as soon as you go to higher dimensions, more invariants appear. Yeah.
Any other questions or comments for
Uh,
Herr Efrain?
el basurto. Yeah. Yeah. Sorry, it wasn't very geometric, but I really like tensor products and stuff.
No. Again, for the students, I just want to express. In class, I will give you the direct formulas for the tensor product, but this is an alternative approach for describing the direct sum, the exterior algebra, symmetric algebra, tensor products. There is this philosophy that Ephraim presented to us today, and it is very useful also that point of view.
Mm-hmm. Yeah.
But now, I understood what you, in your conclusion, that any proof of the volume of the pyramid will involve infinitesimal things.
Yes.
But I mean, come on, Euclid proved that, so he was using calculus then?
No, I mean, how Euclid found volumes of things. He put it into water, and so how many water was placed? I don't know. I don't know how he did it.
Actually, I think he had a notion of limits.
Huh?
I
Wasn't
remember that
wasn't he the guy that
that
irritated someone for saying that square root of 2 was not rational? Who was that?
I don't
I'm,
know.
I'm familiar with some Greek philosopher being like, oh no, but that's not a rational number. So that should be a thing from the devil. And the guy who proposed it, then it was thrown to death or something. A very stupid thing. Mm.
But I mean, if okay, so you say, okay, the way to compute the volume,
Mhm.
I mean, last thing you compute the volume, you put it into water.
I mean, that's how he does things, no?
That's the principle. Okay, that's true. But I mean, we are discussing something different because we don't want the value, we want a formula for the volume.
Yes. Yeah, and
And
exactly.
so that's
Yeah, as
why
Daniel
more
spoke,
different
as Daniel, I think he mentioned, I think Euclid were aware of some for rudimentary form of calculus. Of course, it wasn't the calculus we know and love today, but yeah, some infinitesimal process he was aware of, and maybe he just dissected the pyramid into an infinite numbers of smaller polyhedrons, and then deform it into a cube. I don't know.
And yeah, so also I think what Daniel was saying, I don't know if you did or not, but at least in that time, also to get pi, right? I mean,
Exactly.
they have an infinitesimal polygon, so to speak.
Yeah,
Yes.
basically yes.
Mhm.
No, I say that because I don't know if it was him, but when you prove like the fifth postulate is equivalent to some other stuff,
Oh, okay,
he used like some sort of limit.
right. Some limit of triangles. Yes, yes,
Right, yes. So I don't know if maybe he used something like that or.
yes. I know what you are referring to. I don't know if that idea is attributed to the Greeks. That's my only concern. I don't know that.
And to whom?
Yes,
To the Greeks, to
Ah,
Euclid,
okay.
someone of them. I don't know.
Yeah,
I see. Nice.
yeah. But it's, I mean, I don't know, but I find it very frustrating because why not? But
Yo voy a la papelería y me compro una plantilla y armo los poliedros. ¿Cómo?
how come that I cannot do that in a
Porque
final
tengo esos cálculos.
yeah, it's very frustrating in my opinion. But hey.
Yeah,
Yeah.
no, so it's something good to think about it. Great. And anyone else has a question or a comment? Now, in the meantime, Efrain, you also said that part of this came from which book that you use?
Which one? Yeah. Everything I used was yeah.
I
Sorry.
think that's like a
Yeah.
popular kind of book.
Yeah. Exactly. Sorry. The talk is come. I use the talk for that. I use the book. Sorry. Linear algebra by Stefan Waldman. I mean,
Oh,
everything is in German, but the concepts are clear. Absolutely, all of the talk is coming from this book. So there is not, except the part of the flow, because actually my advisor did that. I just, okay. So if he's seeing the video, yeah, Lawrence, I use your part. But yeah, the rest, the preliminaries, the tensor product, I use this book for there is also the book, where did I find that? Yeah.
but one man is he? Yeah, I think he was here in Colima a while ago.
Stefan Waldman?
Yeah,
Really? That's nice. I mean,
that's exactly what I'm trying to see if he's the one. Yes, he was here. Uh, right. Yeah, he's the one. Yes.
yeah. Yeah, exactly. Yeah, I mean, well, I didn't mention to him that I study in Colima, but I met him like 2 years ago in a meeting
Also,
conference.
so say hi to him for me.
Yeah, but I mean, he's all the way in South Germany, so it's not very often that I go there.
Yeah, but still, I mean, he will not, he doesn't come very often to Mexico, so he will know, he will remember.
Yeah, I hope yes. And I mean, Mexico is freaking awesome. So yeah, And also, the other books I used, well, the other papers I used was, yeah, Fort Meyer, Oliver Fort Meyer, Hilbert's Problem, also in German. Sorry, I mean I'm
What
quite
is the neatness means? The neatness?
Dritt's third.
Third problem. Okay.
Mhm. Yeah.
And
Exactly. So that exactly, that's also where I use.
yeah, and Daniel. So Stefan Waldman, he works in different areas, but one of them is Poisson geometry.
Oh yes,
Okay.
actually the meeting I attended was about quantization. I didn't understand a thing, but hey, I attended.
He was here.
Okay.
Yeah, I was there. I don't know if you know this famous mathematician Simone Good.
Yes,
Yeah, she was also a speaker there.
and her son.
Jan
Her
Good, he
son.
was here in Dortmund actually visiting.
Yeah, he does symplectic geometry capacities and
Yeah, exactly. He actually 2018 he was here in Dortmund because my advisor, my advisor is a very good friend of Simon Good, and then he invited her son. Was visiting for a week or something.
What is
Exactly,
the name of the son? I forgot.
Jan.
Jan Good.
Jan Good. Exactly. This is another source I use, and this is in Christian language, also in English. Hilbert's third problem, Caesar congruence. If someone
Oh,
is
the Caesar that you mentioned, right?
exactly. Yeah, those were my sources. Yeah.
Very nice.
Mm-hmm.
I don't know, but what about the rest? Any questions or comments? Salvador, Moises?
Provided they are awake. Provided they are,
Yeah, here we are.
okay.
Nice.
Yeah. Okay, so fine. Yeah, I don't know. No. Tell us a joke or something, Andres.
Your joke about Charlie Brown and I don't know.
Yeah, I mean, I like to joke about that because I remember that when I was in Colima, I was very bullied because I couldn't speak English. I mean, I still cannot, but I make the effort. Yeah.
Well, if we have no more comments, so Efrain, thank you very much.
Yeah, no, you're very welcome anytime. I mean, I'm going to do this again in July.
Right, so in the workshop,
Yes.
I will see you there.
Mhm.
Now, so how many years more do you have for your PhD?
Well, my contract runs on April, so I need to hurry. Yeah.
Oh, so you will be done
In some, yeah, at some point in this year or
by the end of the year, right?
exactly.
Okay.
Yeah.
So good luck, man.
Thank you. I need it. Yeah.
Right. So if there are no more questions or comments, so Efrain, thank you very much and keep in touch.
Yeah, sure.
Thank you.
Thank you.
Yeah.
Nos vemos.
Nos vemos, Andrés.
Uno
Gracias.
nos anotar en la sección 4.
Representing.
Muy bien. Adiós.
Bye.